Today, we're digging into a pretty radical new origin story for one of the most mysterious phenomena in all of physics, Hawking radiation. And it all starts in a place you would never, ever expect. It sounds like a riddle, right? But the answer is this incredibly powerful physical analogy. It's a new theory that suggests the vacuum of space isn't empty at all. Instead, it might be an active, elastic medium. And if that's true, well, that changes just about everything.
All right, so here's our roadmap. We're going to start with that weird effect you see in a wine glass, and then we'll see how physicists are applying that exact same logic to the edge of a black hole. We'll check the math to see if it actually holds up, and then finally, we'll explore what this all means for our entire picture of empty space. So, let's get into it.
Okay, so believe it or not, our journey into deep space begins right here, inside a glass of wine. We're going to build this entire cosmic theory on a surprisingly common effect from fluid dynamics.
It's called the Marangoni effect. You've definitely seen it. In a wine glass, the alcohol evaporates faster than the water, which changes the surface tension right at the edge. This difference, this gradient, it creates a stress that literally pulls the wine up the side of the glass. Now, the key thing to get here, the really important part, is that the flow isn't being caused by some external force. It's being driven by a change in the fluid's own internal properties. Just remember that.
And now for the giant leap. We're going to take that exact fluid principle and apply it to the most extreme environment in the entire universe, a black hole's event horizon. And the way we do that is by treating the vacuum of spacetime itself as a kind of fluid.
The framework for this is called dissipative vacuum field theory, or DVFT. It models the vacuum as a complex field, which you can see described by the equation here. Just think of rho as its energy density and theta as its phase. You can kind of think of it like the internal rhythm of the vacuum. So in this picture, empty space isn't empty at all. It's more like this calm, structured ocean that fills the entire universe.
And what that means is the event horizon stops being this sort of abstract, magical one-way door. Instead, it becomes a physical interface, a surface, where the properties of this vacuum fluid change, and they change dramatically, just like the surface between air and water.
And this right here is the absolute core of the whole idea. The physics just maps over almost perfectly. The liquid medium in the wine glass, that's the vacuum field. The liquid surface, that's the event horizon. And most importantly, the fluid surface tension has a direct analog, something we can call vacuum tension.
So this is where the idea gets really, really powerful. This analogy isn't just some neat story we can tell ourselves. It's a real mathematical tool. Using this idea, you can actually derive Stephen Hawking's most famous predictions right from the ground up.
Let's just walk through the logic. First, you model the horizon, and you give it a vacuum tension that changes depending on how curved the horizon is. Second, just like in the wine glass, that gradient in tension drives an outward flow of energy. Third, the math lets you calculate an effective temperature for that flow. Fourth, from that temperature, you can figure out the total power being radiated away. And then, when you put all those pieces together, the famous scaling laws that Hawking predicted just fall right out of the equations. It's incredible. And the first big success is a huge one. The model perfectly reproduces Hawking's very famous and very counterintuitive discovery that smaller, more curved black holes are actually hotter. Now, in this model, that isn't just some weird fact. It's a direct consequence of how this vacuum fluid has to behave.
But it doesn't stop there. When you calculate the total power that gets radiated by this Marangoni-like vacuum flow, you get another perfect match to Hawking's prediction. The power goes as 1 over the mass squared. And what that means is that smaller black holes don't just run hotter, they evaporate away exponentially faster.
And finally, if you integrate that power law over time, the model gives you the total evaporation time of a black hole. And, you guessed it, it's proportional to the mass cubed. The entire thermodynamic behavior, its temperature, its power, its lifetime, it all gets derived from this single, coherent picture of a vacuum fluid in motion.
So, okay, the math checks out. That's huge, but the real power here, the true innovation, is the physical story it tells, and it's a story that goes way beyond the familiar tale of virtual particles.
This slide really lays it out. On one hand, you have the standard story we all learned. Virtual particles popping into existence, one falls in, one escapes. But in this new DVFT picture, it's a deterministic physical process. The continuous vacuum field is under stress at the horizon, and the radiation is just that stress relaxing outwards. No random particles needed. You see,
Unlike the virtual particle story, this model gives us direct physical answers to old questions. Why is the radiation the same for everything? Because it's a property of the vacuum itself, not some specific particle. Why is it thermal? Because it's a smooth relaxation process, kind of like a stretched rubber band releasing its energy, not a bunch of random events. And it perfectly explains why a smooth, uniform horizon wouldn't radiate at all. No gradient, no flow. Simple as that.
Let's be really clear about the shift here. This isn't just finding a new way to get the same answer. It proposes an actual physical mechanism. It moves the explanation from a kind of statistical accounting trick with virtual things to a tangible, causal process happening in a real, physical medium.
And this brings us to the most profound conclusion of this entire line of reasoning. Because this isn't just about black holes anymore, it's about the fundamental nature of what we call empty space.
This one sentence is the powerful thesis of the entire model. It reframes a deep cosmic mystery as this necessary, almost normal response of the vacuum to the stress of a horizon. It's not a quantum miracle, it's vacuum fluid dynamics. And maybe the most compelling part of all, this model isn't just a one-trick pony. As you can see here, it might actually unify several other really strange quantum vacuum phenomena. The Casimir effect, the Unruh effect, they could all just be different versions of the same core idea, the physics of a stressed, fluid-like vacuum.
So, the ultimate takeaway here is a pretty profound one. The existence of Hawking radiation might not be evidence for a sea of fleeting virtual particles. Instead, it could be the strongest proof we have that the vacuum, that nothingness, is actually an active, structured, and elastic medium, one that's capable of being stretched and stressed and relaxed.
And that just leaves you wondering, right? If empty space isn't empty at all, but is this complex physical medium, what else could it be doing? What other phenomena, from dark energy to cosmic inflation, might just be different behaviors of this active, elastic vacuum? What we once thought was the end of the story, empty space, might just be the beginning of the next great frontier in physics.